Thank you. And in particular, I'd like to thank my fellow organizers for inviting me to give a talk. This is probably my last conference in representation theory, at least as speaker, and it's very nice to be one that I helped start, and which I'm quite proud of. So I'm going to talk about higher homological algebra. They and some calculations I've been doing. It's in conjunction with the projects with this group of authors, which I don't have time to pronounce because I only have 10 minutes. So I'll just go straight into the setting. So since we're doing higher homological algebra, we start in some module category over some algebra lambda, which is D representation finite. What that means in practice, it has a D cluster tilting subcategory, which I won't tell you what it is. You can look it up quite easily. But it does have finitely many indecomposables. That's the D representation finite part. It does automatically contain all the projectives in mod lambda. And it has, most crucially for our purposes, this one will have D Auslanderreiten sequences. It's not always guaranteed, but it does. It's also D abelian. Now, the Auslanderreiten sequence, just like a regular Auslanderreiten sequence or almost split sequence, you take some indecomposable x, you have a translate of x, and you have an extension, but in this case with the D middle terms. That's the D part. If you think that higher homological algebra is not for you, then as Carlo suggested, set D equal to 1. And actually, for once, my talk will still be interesting. Now, the question I want to do is I want to compute or find all maximal tau D rigid pairs in the D abelian category, big D. So I'll motivate why, but to start with, let's just look at the definition. So maximal tau D rigid pairs are pairs consisting of two modules. One, the module T, is tau D rigid, meaning there's no maps from T to tau D of T, or no non-trivial maps. And the other one, P, is projective, and there's also no maps from the projective to the tau D rigid. I also said it's maximal, and there is some sense of maximality, which I won't tell you, because it doesn't look nice. And for D equals 1, these are really support tau tilting pairs, and we know a lot about them. They are really cool. They're in correspondence to torsion classes, for instance. Another simple fact about them is that if you take the number of summands, of indecomposable summands in T and in P, and we're assuming these are basic, you get the number of indecomposable summands in the algebra as a model of itself. This goes out the window once you get to higher D. So one motivation, a simple one, for being able to calculate all the maximal tau D rigid pairs is just simply to check. Do we have anything similar to this? There are other reasons why you want to calculate all of them, looking for some counterexamples, but for now, let's look at that. And for the purpose of this, because we're actually doing calculations, we will restrict to the higher Auslander algebras. For example, we could look at mod A42. That is actually just the Auslander algebra over of the module category of a linear Lincoln type A4 algebra. It has a D cluster tilting subcategory, specifically a 2 cluster tilting subcategory, which looks like this when you draw the AR quiver. And in this, if you take these nodes marked in orange, we get a tau D rigid object or module, and here in blue are all projectives, and together they make a maximal tau 2 rigid pair, because D is equal to 2 here. Now, that is one. There are many others. So I want to do this with a computer. This shouldn't surprise anyone who's met me. And so to do that, I need some ways of simplifying the problem. And the first one is a classic one. Look at the indecomposable summands. It turns out we can translate the criteria for being a maximal tau D rigid pair to just holding for pairs of summands from T and P. And if you then just make sure that you can't add any other indecomposable summands and still have a tau d rigid pair, so this the whole, well, then you're actually maximal. This doesn't hold in general, but it holds in this case because it's a nice enough category. So that's one component. I just need to look at indecomposables. And the other thing that makes this possible to do with a computer is that there is a nice combinatorial model for the indecomposables, which tells me things about, for example, homomorphisms. It's due to Oppmann-Thomas, and it has also been extended to high Nakayama algebras by Hasso and Kilsummer. And with that, I'm ready to plug all my information into a computer, right? I did. And then I realized that just because you can plug it into a computer doesn't mean that the computer can do anything sensible with it. And my first attempt at writing an algorithm did work. It was very slow, and my computer crashed. So I needed to be smarter about it. And this is where the NP-completeness comes into the problem, because to understand how to compute this in an efficient way, we need to abstract a little bit. We consider a graph, and remember, we are looking for maximal tau rigid pairs. And this graph, it consists of, basically here is everything that could go into the first part of the pair, into the tau d rigid part. And then I put an extra copy of, so everything, all the indecomposables in D. And then I put an extra copy of the projectives to represent the things that can go into the P part. And then I add edges. So this is an unoriented graph, or undirected graph. But I add edges wherever two vertices are compatible, so they could be in a tau d rigid pair together. So and then I look for a maximal fully connected subgraph. So since it's fully connected, meaning, so here's an example of a maximal fully connected subgraph that is not from a graph that I consider, but still, it's a nice little example that I saw from Wikipedia. You see every vertex has an edge to all other vertices. That's what I mean by fully connected. And since it's fully connected, that actually means that all the vertices, if I look back to the mass indecomposable modules, are compatible. And if it's maximal, I can't add anything else. I can't add any other indecomposable. So maximal fully connected subgraphs actually correspond to maximal tau d rigid pairs. And it turns out finding these, they're not actually called maximal fully connected subgraphs, they are called maximal cliques. And computer scientists have been studied this. Finding maximal cliques, I lied in my abstract, it's an NP hard problem, it's not an NP complete problem for technical reasons, but it's connected to one. So this is something that people have studied. And the best algorithm that's known has been known for 50 years. It's called the Braun-Kerbosch algorithm. And because it's been known for 50 years, it has really good implementations. So now, instead of, I can go back, plug all this information into my computer, turn my problem into a graph problem, and throw a nice Python library at it. I use NetworkX. It has the implementation. And I actually get results. So here are a number of maximal tau d rigid pairs. And I'm just doing some of my results here. I'm doing the higher Auslander algebra with over 4 nodes, and for increasing D. And we can see how pairs of various sizes, how many appear. I'm just counting here. So in the middle, we'll have the ones with the expected number of summands, the same as number algebra. For D equal to 1, good, everything works as it should. I even have a Catalan number, so I'm happy. For D equal to 2, we still have this, that the maximal tau d rigid pairs all have the expected number of summands. But if I go to D equal to 3 or D equal to 4, there appears examples with too few, in scare quotes, summands. But there are never more. So I'll just finish by some questions that I would love for someone to consider. First of all, is the size of the algebra actually an upper bound for the size of the maximal tau d rigid pair? I don't know. I haven't found any counterexample. I would love to find a pattern to the number of pairs. And also, why are there so many with too few summons? And finally, I was wondering, since we know about, well, tau tilting theory, and not to mention higher tau tilting theory, but especially tau tilting theory, could we use some of the information we have to say something about the maximal clique problem? Thank you.